Good morning, classmates and Mr. Gopi. Today we're gonna present about infrared spectroscopy by me, Donna, and Jasmine, Katrin, and Audrey. Infrared spectroscopy. In infrared spectroscopy, a sample being analyzed is irradiated with electromagnetic wave in the infrared region of the electromagnetic spectrum. A spectrophotometer detects the intensity of the wavelength of infrared radiation that passes through the sample. It is useful because all organic molecules observe the radiation in the infrared range of the wavelength. The energy is observed corresponds to the change in the vibration of the bond between atoms. The bonds can vibrate by stretching, bending, and twisting. They have a natural frequency at which they vibrate. When irradiated molecules with energy that corresponds to this frequency, it stimulates larger vibration and energy is observed. This is called resonance frequency. Each vibration will observe characteristic wavelength of infrared radiation measured by the unit wave numbers. For example, the amine group observed in the range of 3300 to 3500. Therefore, we can identify the presence or absence of different functional groups from the absorbance pattern of an infrared spectrum. We can use the characteristic infrared spectrum of an unknown compound to identify it by fingerprinting from a database of known spectra. Some characteristic absorption ranges and appearance of the peaks are shown in the table here. The absorption bands overlap considerably, so we need to use a variety of techniques such as NMR, infrared spectroscopy, and mass spectrometry to work out the structure of a new organic compound. As well as their wave number bands, particular absorbance have characteristic widths such as broad or sharp peaks, and intensity such as strong or weak on the infrared spectrum. For example, the presence of hydrogen bonding makes the absorbance of OH bonds in alcohol and carboxylic acid broad. By contrast, the CO double bond in carbonyl group have a strong, sharp absorbance peak.
This is the infrared spectroscopy graph for esters. It has a lot of pointed points and it looks like icicles. The diagram on the bottom right shows a CH bond. It has a wave number which lies in between 2500 per centimeter to 3300 per centimeter. Its peak lies on a wave number of 3000 per centimeter and it has a very broad absorbance. The diagram on the bottom right shows a CO double bond. It has a wave number which lies between 1640 per centimeters and 1750 per centimeters. It has a peak at a wave number of 1750 per centimeters. It has a strong and sharp absorbance. The diagram on the bottom right shows a CO single bond. It has a wave number which lies between 1040 per centimeters to 1300 per centimeters. It has a very strong peak at 1250 per centimeter.
This is the infrared spectroscopy for carboxylic acid. It has a round curve followed by sharp peaks, which resembles a mountain. In the carboxylic acid functional group, the C double bond O lies in between 1640 waves per centimeter and 1750 waves per centimeter. In this graph, it is shown that its peak is at around 1750 waves per centimeter. The characteristics of this bond is that it has strong and sharp absorbance and it has a strong peak. The range of the infrared spectroscopy for OH bond lies in between 2500 waves per centimeter and 3200 waves per centimeter. In the graph, the OH bond peaks at 3100 waves per centimeter, and its characteristics is that it has sharp peaks and broad absorbance.
This is the infrared spectroscopy graph for alcohol. It looks like a ghost with a peace sign. The diagram below shows an OH bond. Its wave number lies in between 3200 per centimeter to 3600 per centimeter. It peaks at 3400 per centimeter and it has a very broad absorbance.